right, so we've got a nozzle. We're given some inlet conditions and some outlet conditions, and this problem is a little bit different because we're given the amount of heat loss from the nozzle. So first of all, they tell us that the heat loss is 6.5 BTU per pound mass, so that's a lowercase q, little q, and it's also going to be a negative number since it's leaving the air, leaving that control volume, if you take the control volume to be the air that's passing through that nozzle. And then we're supposed to find the temperature in the area. Now, I do want to point out that for a nozzle, you usually do ignore the heat transfer because it's typically negligible, especially when you're looking at the changes in enthalpy and the changes in kinetic energy. Those terms are going to be much, much bigger than the heat transfer term. But since the problem statement, since they went ahead and went through the trouble of giving us that heat transfer, we're going to go ahead and use it in our analysis. So the first thing that I'm going to do is I'm going to apply my mass balance. So the sum of the mass flow rates coming in and out is equal to, or this dmdt is equal to the sum of the mass flow rates coming in minus the sum of the mass flow rates going out. And if this thing happens at steady state, that dmdt goes away and the mass flow rates at state 1 and state 2 are equal to one another. And I need to do that mass balance because I need to use what I found here to plug into my energy balance. So I've got an open system because I've got mass coming in and mass going out, and there's some things that can cancel out, right? My DEDT can go away because this is occurring at steady state. I don't have any power generated or used for this nozzle. I don't have any potential energy changes, so the GZ goes away, and so this is the first law that I'm left with. And the mass, I've only got one inlet and one outlet, and that mass flow rate at the inlet and outlet are both equal to one another. So I don't even have to put a subscript there. So this is my first law. This is what it boils down to. And if I divide through by that mass flow rate and then solve for H2, I can get things in terms of little q, because little q is equal to q dot divided by m dot. So where I'm going here is if I solve for H2, I can go back to my ideal air tables and I can interpolate for the corresponding temperature at that H2 value that I solve for. So if I plug in my numbers and I watch my units there, I get 121.24 BTU per pound mass. And if I go to my ideal air tables and interpolate for the temperature at H2, I get about 507.4 degrees Rankine. Now I'm going to go solve for the area at state 2, and for this I'm going to go back to that mass balance, and if I assume 1D flow, I could put the mass flow rates in terms of the area, the velocity, and the specific volume. Furthermore, because I've got air, I typically assume air behaves as an ideal gas, but it's really easy to justify that assumption by calculating the reduced pressure. So we said that the reduced pressure, if the reduced pressure is less than 0.1 in this class, we're good with making the assumption that that you've got an ideal gas. And I can get to watch your units here, but you can look up the critical pressure in your tables. It's 37.2 atm, and if you convert that first pressure to PS or to atm from PSI, you get a reduced pressure of 0.09. And because the pressure at state 2 is even less than the pressure at state 1, the pressure at state 2 is less than the pressure at state 1, so you went from 50 psi to 14.7 psi, then you can reason out that the reduced pressure at state 2 is less than the reduced pressure at state 1. You don't even need to calculate it. You can already tell just by looking at it. So by making the assumption that you've got an ideal gas, you can put your specific volume in terms of RT over P, and then solve for the area at state 2. And then if I plug in all my numbers, you could see my units just kind of cancel out, and I ended up getting 0.048 feet squared for the area at state 2. All right, hope that was helpful. Thanks for watching.